Good afternoon, students. So we are back here, and now today we'll talk further about the designing of composite materials. So by now, what we have learned. So by now, what we have learned is that we can predict the various properties of unidirectional composites. So we have seen that you can predict the density of the unidirectional composites using the simple rule of mixtures. You have used the rule of mixtures for finding out the longitudinal modulus, which we say is EL, given by this expression here. And we have also found the modulus of the material across the fibers, that is along that transverse direction, which we say is given by this expression. So we have this EL and this is ET. So this EL is also referred to as the upper bound because it gives the higher values, and also called as the Voigt modulus, and the ET is given as also the lower bound modulus, also known as the Reus modulus. We have also seen lastly in our lectures that what is the concept of minimum volume fraction, critical volume fraction, the load sharing concept between the fibers and the matrix, the significance of EF to EM, the ratios, that is the stiffness ratio of the fibers to the stiffness, the ratio of the stiffness of the fibers to the stiffness of the matrix, and how does it govern or how does it influence the stiffness of the resulting composite material. So I can say that to this extent, to the information required in this course, we are now familiar with the basic terminology that we have used in the case of composite materials, and then only limiting our discussion to the unidirectional composite materials. Now going forward, so this is a simple Excel output. What I have done is that we are just going to graphically observe this EC and ET, or EC, that your EL and ET here. So what I have done, I am now plotting on a modulus versus density chart. What I'm doing is that I'm taking the matrix material as epoxy, which is located here, the blue dot, and I'm taking the fiber material as glass fibers, which is located here in this black dot. So we have this here, and then what we see here is that these dots that you observe here, the green ones and the red ones here, they are actually these ones. This is actually, we have predicted the upper bound modulus, means the longitudinal modulus of the composite materials, which is made by combining epoxy and a matrix and glass fibers as a reinforcement in various volume fractions. So you have this 0.1 volume fraction going up to 0.5, 0.9, and this is 1 means only glass fibers. Similarly, what we observe here, the green dots, they are the lower bound modulus values, means given by the transverse modulus values for the same composite material made using epoxy as a matrix and glass fibers as a as a reinforcement, which simply means that whatever composite material that you create, whatever GFRP, now you can call it as GFRP because it is actually glass fiber reinforced polymer, whatever reinforcement, whatever volume fraction of glass fibers is there between in the composite made by epoxy and glass fibers, the properties of the resulting composite that you form here will lie between these two bounds. So you have the upper bound modulus and the lower bound modulus, and depending upon the values of volume fraction that you use, the resulting material may lie anywhere between this zone. So I can say this is the zone in which the resulting composite material properties will lie. We have already seen that the upper modulus or the longitudinal modulus is very accurately predicted by EL equation, but the prediction of ET that is the transverse modulus, is not very accurate. And what we see practically is that you have higher values of transverse modulus obtained experimentally than what you are predicting in our previous expression. So that is why it becomes important to us to understand that when I combine epoxy and glass fibers in various volume fractions, the resulting composite material will have properties some in between this zone only. So it cannot go beyond it cannot be more than this, or it cannot also be less than this. So this is what we see here. This can be very simply done using a very small Excel program, which I'll share with you during our assignments. Okay, so let's come to by now we have the information that what is a composite material, specifically UD composite, and we now know that how we can predict the properties. Now comes the question that when you want to create a composite material for a particular application. So if you go back to the definition of our hybrid material, we have seen that hybrids are designed for some particular engineering application. So let's say the engineering application happens to be that you want to make a beam of minimum mass and stiffness is the constraint, and for that purpose what we see here is that the present problem is that the beam right now is made up of an aluminum alloy. So if you look at this modulus versus density chart, we observe that right now the material that you're using here is here. So this is the material aluminum alloy, which is the present material of this beam. And we can see that where does it lie? That it lies somewhere around 2.8 as the density, and around 70 gigapascals as the modulus. So this is the material which we are currently using. Obviously, it's a monolithic material. The question we want to understand, or the thing that we want to understand by this particular example is that can we improve upon the properties? Can we make the beam still lighter for the same stiffness by replacement of the material, by replacing this original material, that is aluminum alloy, with some hybrid material or a composite material? And that's what we want to understand with this example. Let's say we have two options here. Means that it is possible for us to continue using this aluminum alloy as our material, or I can combine this aluminum alloy with, let's say, the aluminum alloy. Aluminum will be the matrix material, and I can put alumina fibers into that. Or the second option is beryllium, that is, I can combine beryllium with aluminum alloy. The question is, which one is better? So this figure simply answers this question very simply, and this does not need any explanation if you have understood the concept of material indices in our earlier discussions. And what we observe here is, what are these lines? These lines are lines of slope 2, and what we find is 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the value of what we call as the index, that is what is written here as criteria of excellence, that is second root E by rho. So obviously the better materials are located at that position where the index root E by rho is higher. That way beryllium happens to be a very good material, but you cannot use it simply because of its properties, that we cannot simply use beryllium fibers here. Aluminium lies here in this case. What will happen, that these two regions that you find here, this region and then the second region, so when you combine aluminum with alumina, the resulting properties will be in this zone, and when you combine aluminum with beryllium, the resulting properties of the composite can be in this gray zone. Now it's very easy for us now to say that which one will be better. Obviously we can say simply here that combining aluminum with beryllium will be creating materials in this zone, which may be, now if you look at a material here, obviously this material is better than the parent material in forms of its particular criteria of excellence, or what we call as the material index. Now this obviously is valid only for this particular application where minimization of mass for a beam is required. If you want to minimize the mass of a panel, or if you want to minimize the mass of a tie rod, these lines will change. Thus, then you'll obviously use lines of slope 1 or slope 3 instead of using lines of slope 2, and accordingly the result will change. But for this particular application, we find that combining aluminium with beryllium is a better option, and this is precisely what is available to us. So you already have a commercial alloy known as LBmet, which contains 62% beryllium and 38% aluminium. So these two metals, aluminium and beryllium, are mutually insoluble. Mutually insoluble means they will not form an alloy here, and that is why they will create a two-phase composite of aluminium and beryllium with root E by rho of 6.5. That means with around 62% beryllium, it will be lying somewhere here. 62% beryllium will be lying here, somewhere here, and it creates a better material than aluminium alone. So this is what we have seen, that combining two materials to form a composite material generates a new material in its own sense, and we can then say that that composite material will have its own properties, and specifically tailor-made properties, and we will see that what is the meaning of that. Obviously, what we have also seen is that the material that you are talking about, composite material that we form here, is kind of not a isotropic material, because if it is a unidirectional composite, it has properties different in even the two directions that we are referring to. That is, along the fibers it has a different property, and across the fibers or transverse direction it has some different property. So you create an isotropic material by combining two macroscopically isotropic materials of aluminium and beryllium. So that's precisely what we gain by creating composite materials here. Okay, let's go back to EduPack. So in CES EduPack, the version that you may have with you may not have this option available of creating hybrids, but the full version of that gives us a capability. So what we observe here is the same thing which we have seen already, that I have taken epoxy here. So you find here epoxy. This is actual data plotted here. So epoxy simply is this blue dot, and when I combine this with glass fibers, so the glass fibers which are E grade 0.4 to 1.4 microfilaments, so they are located here. So when I combine them, in various volume fractions, so we get these orange dots. So this is the properties of the resulting composite material, and they occupy different spaces. So for our information, I have just plotted one index line here, and we create material. We try to fill up that zone, this zone, which was earlier unfilled. There were no materials available in this particular location, and that is how creation of a hybrid in the form of a composite material has helped us in filling up the vacant spaces in the material property space. On the same lines, what this next figure shows you, again an output of CES EduPack only, that now I compare the same matrix material, that is, I am still using epoxy resin as a matrix material, but now I say that I will try to see that what happens when I combine them in two different ways. So I can either combine this epoxy here with this glass fibers that we are available here. So glass fibers are here in this purple dot, or I can to form a composite. So this orange ones will be forming a composite of epoxy plus glass fibers. Or what else I can do? I can combine the same epoxy resin and form a CFRP. So I have this carbon fibers. Now I have carbon fibers, high modulus carbon fibers, represented by this red dot here. So when I combine these two, when I combine either epoxy with glass fibers, or when I combine epoxy with the carbon fibers, the results are clear to us. So the trajectories are here. So when you combine epoxy with carbon fibers, the resulting properties may be on this red trajectory, and when I combine epoxy with glass fibers, the resulting properties may be on this blue trajectory. So the dots here represent the variation of properties according to the simple volume fraction. And what I have done, what we have done, we have just plotted lines of slope 2 here. So we have 1 line, 2 line, 3 lines. And obviously in this case we understand here that it is better for us to combine glass fibers it is better for us to combine carbon fibers with the epoxy, that is creating a CFRP, maybe giving you a better product in terms of our objective of minimization of mass for a beam. When I combine epoxy resin with glass fibers, the results are not as good as when you create a CFRP. The cost may be a reason why you do not want to go for a CFRP here instead of a GFRP, but that can be taken care of, that we can see when you go to multiple objective problems. But right now cost minimization was not our objective. Our objective was only to talk about minimization of mass, and obviously then we say that if I combine this epoxy with this carbon fibers, the resulting composite material will behave better than when I combine epoxy with glass fiber. So that's what we conclude from this is the same example here. Okay. Now, just to sum up what you can do with the help of creating composite materials is that what we observe here is that on this material property chart, which is modulus versus density chart, we are observing that the envelopes that you observe here, which are somewhat not highlighted, which are somewhat hidden here, and these envelopes, the orange one and this blue one, which are highlighted here, this one, the orange one is for MMCs, that is metal matrix composites, and the blue one is for PMCs, that is polymer matrix composites. So what this chart is simply telling us is that by creating MMCs, that is metal matrix composites, or by creating PMCs, that is polymer matrix composites, we have filled those areas of the material property chart which were not filled earlier. So like this was for polymer, so this location was vacant, there was no material here, so we have created new materials here. Similarly, by creating MMCs, you may see that this is the range which we have created, which was not filled earlier with the help of only metals. Similarly, when you look at it on a strength versus density chart, again a similar observation is made that you have created materials in this zone with the help of PMCs, polymer matrix composites, maybe CFRPs and GFRPs. Then this zone was earlier unfilled, we do not have material here. And similarly, MMCs are also created here. Okay, now let me sum up this discussion or end this discussion by talking about one more concept of anisotropy. We already have by now known that unidirectional composite materials, they are anisotropic in a way that you have different properties in different directions. Though we have already seen that you have EL as the longitudinal modulus given by this expression, and we have ET as the transverse modulus given by the second expression here. This EL is also called as the upper bound because it gives you a higher value of modulus, and ET is also known as the lower bound modulus. And let us see, we define now another term called as the anisotropy ratio, known as RA. So anisotropy ratio means what is the ratio between, simply it's just a ratio of EL to ET. So it's just simply a ratio of EL to ET. So when I take the ratio of EL upon ET, I get this resulting expression, which we say is telling us about the anisotropy ratio, that how much is the anisotropy when I compare these two directions. In between these two means when you are loading somewhere in between, the longitudinal and transverse, the values may slightly vary, but right now we are talking about only unidirectional composites, and when they are loaded only along two directions, either they are loaded along the longitudinal direction or either they are loaded along the transverse direction. So when they are loaded along the longitudinal direction, the modulus is given by this expression. When they are loaded along the transverse direction, the modulus is given by the second expression. And the ratio of the modulus EL to modulus ET is what is now given here as the anisotropy ratio RA. And when I just write and solve these two expressions, this is what I get, that RA is nothing but VF square. We understand VF is volume fraction of fibers plus VM square plus VF VM into EF1 EM plus EM by EF. So this expression gives us that what will be the ratio of anisotropy between the two directions. So this discussion, this lecture here, I understand that it sums up my discussion on hybrid materials of the type of composite materials and what we gain by creating composite materials, which we say also as a category of hybrid materials.